All right, so this probably looks like a lot of words and numbers on this page. We're going to break it down into pieces. Before, which was in chapter 2, you already learned how to do this factor label method, unit conversion, whatever you want to call it, dimensional analysis. And you learned that you can take grams and that you can take the molar mass from the periodic chart. Now this one is diatomic. There are 7 diatomics. And so here's hydrogen right over on this side. That's 1.01, but since it's diatomic, there are 2 stuck together. So that's why that's 2.02, and a square is 1 mole. And then you take it and you convert from moles of that. We got to bring the moles down, and then we turn it into molecules of H2. We use Avogadro's number, and the number itself goes with like the molecules or the atoms, the particles. That's the big number, and then it's always in the 1 mole. And here's the key difference of what we are about to change to. We were given an amount of hydrogen gas, and we had to find an amount of hydrogen gas. So all of these are all H2. And here's the math on it. Just as a reminder, I'm putting in your calculator. You're going to take 3, you're going to go times 6.022 e to the 23rd, divided by, don't forget to divide by the 2.02. You don't have to include the ones unless you want to. And so that gives us our 8.94 because this is 1, 2, 3 sig figs. And then times 10 to the 23rd. Don't lose that 23rd on that right-hand side. So you've done this all before. You've done homework sets on it. Just got to bring that back because it's been a few weeks since we've actually looked at it. All right, so now we're going to look at this second part. And this is the only thing that's really changing. It just gives us even more options. Is that we start with this H2 gas, and now we're going to find out something about O2. So the only way to switch between one element and another is with this chemical reaction, and it's by looking at the coefficients. So if I do the H, that's how many H's there are compared to how many O's. That's an understood one there. So you'll notice that, again, I start with, the only number I have is that 3 grams. So I start with that one. Then I go from grams of H2, so those would cancel. And then I have my moles. And then at this point, I'm switching to oxygen. And then notice that grams of H2, moles of H2, moles of H2, moles of O2, moles of O2. So we're left with this molecules of O2. Let's remind ourselves where all the numbers came from again. This was in the problem. This came from the periodic chart over here. And it's diatomic, and so that's why it's 2, and it's grams in a mole. And then this section is the new piece of information that you can look at those coefficients on the front. And here's our equation up here. I had the 2 with the hydrogen. That's why there's a 2 there. And then I have a 2 with the oxygen. And that, I mean, a 1 by the oxygen, and that's why there's a 1 there. And then again, this is just Avogadro's number right there. And the 1 always goes with the moles. So now I can take that same thing, the 3 times the 6.022 e to the 23rd, divided by 2.02, divided by 2. So that gives us 4.46 times 10 to the 23rd. We have 1, 2, 3 sig figs, so I need 1, 2, 3 sig figs. So that's how we switch from one thing to another. So it's pretty cool. It's not too hard. Here's the other example. You can also convert from, this is supposed to be H2O, so I'm going to correct it. On mine, yours should be corrected. You can also convert, so right here we converted between reactants, but you can also convert over to products, which is what this next step is. So you'll notice that, again, we started with grams of H2 divided by grams of H2, that number's from the chart, to moles. Then our moles cancel, and then that's when we switch to moles of water and moles of water. And we're still water when we get to the end. So we swapped it up. And the big important change is right here. And again, now we're looking at the hydrogen as compared to the water. And you see that's 2 to 2. or it's kind of like being 1-to-1. And when we put that in the calculator, I don't know if you can see, but it's the only difference between these two equations, this is 1/2 and that's 2/2. So this number here is twice that number, which makes sense because there's a 2 in it. And so whenever we turn something into a product amount of something, and again, it's the product amount, like you're trying to make something new, we call it a yield because we made it. And the type of yield is a theoretical. So what that means is in a perfect world where you have perfect pressure, perfect purity, perfect glassware, perfect technique, perfect everything, we would predict this. Now, if you actually wrote some journal articles and claimed to actually get that yield, they're going to look at you like you're crazy because you can't really hit the 100% yield. It's just impossible to do it. People won't believe you. It's that impossible. So theoretical yield is kind of like, it's like your maximum that you could ever get. And you can use it to tell like how good your reaction is, like how good the amount of products that you predict, like if you're close to being really efficient in the amount of reactants that you've used, making the amount of product.